So hello everyone.
Hi everybody.
Today's webinar is about to start. I am Isabelle Girard, Marketing Manager at ProSim. I'm here with Quentin, Process Engineer at ProSim. Today's webinar will last about 1 hour and the topic is how to reduce water consumption in industry using water pinch analysis. The webinar agenda is organized as follows. I will start with a short introduction about ProSim. Quentin will then do the presentation with a short demo with Simulis Pinch. We will end with a question and answer session. So let me introduce you with ProSim and who we are. Our skills and competencies lie in the field of process system engineering. Our mission is to guide our customers to efficiency through process modeling and simulation. We have a double competency in chemical engineering and scientific software development. We propose a consistent suite of software that we develop. I will not get into the detail of each software today because this is not the purpose of this webinar. Just know that we have a large range of process simulation software depending on your needs and your industry. And you can find more information about each of our software on our website, www.prosim.net. ProSim is a chemical engineering software editor, but not only. We also provide services, training, maintenance, and support on our software. We also do process studies through modeling and simulation. We can also customize our software for our customer or develop specific software application. And we are also doing support and maintenance of legacy codes, of course, in the field of chemical engineering. So thanks to a large range of software and services, we covered many industries. For each industry, our solutions are used by engineering companies, production companies, and equipment manufacturers. Our headquarters is based in Toulouse, France. This is where we are right now with Quentin. And we have a subsidiary in Philadelphia in the US. We also built a strong network of partners and distributors worldwide. And today we have more than 1,200 customers in 75 countries. So this is it for the short introduction about our company. And I will now let Quentin do the presentation.
I will present you the water pinch analysis. Also named water pinch methods, to reduce the water consumption of a factory. The main objective is to reuse the wastewater from the process. So we will talk about reuse with the water pinch method. So before starting the presentation of the water pinch analysis, just a point about the situation. So today we are talking about transition, inevitable transition, in order to be more efficient from a water consumption point of view. Why? First, because of the degradation of aquatic environment. Then because of the climate change and global warming of areas that are more affected than others, and for those that water storage decrease drastically, and also because of human growth that will be a few billion more in few years. So all human activities, whatever it will be, have to adapt to this new situation with more limitation, more restriction, and conflict of water use. Water in quality and in quantity sufficient will no longer be available every day of the year. So over the last 20 years, the environment impact of industrial sites has become a growing concern. Governments have introduced new environmental protection laws and have means necessary to enforce them. We are in a circular economy approach which is used to reduce water extraction and ensure this transition. So what does it mean for an industrial? From industry point of view, the main indicators are the direct cost of water use. These direct costs are the visible part of the iceberg. Direct costs are the costs for supply and discharge of our process. They are the cost of material cubic meter of water, but also the cost of treatment. So reactants, energy cost, installations cost, operating and maintenance cost. Behind the hidden part, the hidden face, there will be indirect cost, like indirect cost on performance of the factory. We will have restriction for a summer period and therefore a decrease of productivity. We will have problem of non-quality produced because the water we will use is no longer the same, or we will have risk and impact on environment, health risk, trial and justice cases. It will be necessary to adapt to the new restriction that will be more and more restrictive, and it will be more and more difficult to obtain administrative authorization. And also on marketing aspect, water efficient competitor will obtain the adhesion of customer because the ecological and environmental image will be more and more important for society. So there are many things behind that make this transition crucial for future and for industry. So actually, the current situation is the following. In a lot of factories, the water is coming from a water treatment station, a water treatment unit. This water can be extracted directly, but generally this water comes from a water treatment, which can be the one of the factory or one of outside of the factory. On plant point of view, the water is used in parallel. That means we use in parallel the water for the different units and for the different processes, and then the water leaves the plant. Generally, the water streams are mixed and fed a wastewater treatment unit. This final treatment on wastewater can be the one of the factory, but also can be the one of the city around. So globally, there is no performance at the level of the water uses on most industrial sites. That is to say that there is no reflection on the water quality needed for each process. Often we used domestic water, fresh water, sometimes drinking water for all processes without thinking if we could use less clean water for some units and reuse other streams. So we cannot stay in this current model, which is technically and economically unsuitable for this transition. So to design our new model and our new future, you can improve efficiency on two ways to reduce the consumption. The first way is to improve the use. And the second one is about water management. And water management is linked to the conception of a new water network that consumes less water. For the first way, the improvement of the water use, we have different things. We can improve the performance of water treatment units and wastewater treatment units, to limit the water catchment and limit discharges. But you can also improve the performance of each process. So concretely, it means that to have more environmental and more ecological processes that use less water on our process. This first way of improvement, are rather technological. We change the equipment, the facilities, for the best technologies, more efficient on water consumption. The second way, it's about the presentations today. It's at the level of water management. The goal is to introduce reuses in the process. The recycling within the process is used to reduce the water inputs of the factory and also reduce the discharges. So on this picture, we decided to represent the sorting of the effluent. So we will sort the effluent that are very charged, very loaded and contaminated, and perhaps collect them in order to retreat them by a dedicated factory, for example. And on the other hand, we will design reuses. These reuses may be direct reuses without regeneration, without intermediate processing, intermediate treatment, or it could be a reuse with a treatment, a regeneration upstream of the reuse. For sure, you will say me, yes, it's good to reuse, but how we can find relevant reuses and how we can do to create this water network efficiently. And well, it's very simple. ProSim has developed a tool which meets these needs and meets this demand. And this tool, it's called Simulis Pinch. I will talk about this software today. The main objective of the tool is to offer you a new water network according to the different needs you have on the different units and according to the different discharges of your process. So then the outline it's very simple. It is first a short analogy between the water pinch, also called the mass pinch analysis, and a comparison with the energy pinch analysis, also named thermal pinch analysis. And we will see that there is a direct analogy between the two methods, and the same concepts are used in both fields, energy and water. And then I will present you the water pinch method, how we can do to build the curve of the analysis, what are the results of the method, and I will finish with a demo of Simulis Pinch before a short conclusion. So I start with a reminder about the pinch method applied to the energy field. So for a process, whatever it may be, we can find heating needs and cooling requirements. That is to say that there are hot streams that need to be cooled and cold streams that we need to heat. So to achieve this heating or cooling, we used hot utilities, for example, high vapor steam, medium pressure steam, hot water, and so on. And to cool down the hot stream of your process, you need cold utilities like cooling water, glycol water, and different other cold utilities. With the pinch method, we called a hot stream a sink because we draw energy from the stream. And for cold stream, we name it as sources. So then the principle of the pinch method is to draw the curve composed of the cooling requirement and heating requirement of the process. For a process, it is necessary to identify all the streams that we need to heat in our process, which are currently heated by hot utilities, and identify all the streams we want to cool down, the hot stream. And then just draw the temperature curve according to the amount of heat for all process streams. So by accumulating all these needs, it is possible to create a hot composite curve and a cold composite curve. So that means that if we take all the heat duties of all the streams, we will have the actual needs of cold utilities for hot streams and the actual needs of hot utilities for the cold stream of the process. And so then the pinch method is very simple. We take these just two curves and we move the curve of the cold stream under the curve of the hot stream until we reach the pinch point. And this pinch point is defined by the user. It is exactly the same principle as an heat exchanger with a hot stream and a cold stream. In order to make the heat transfer, the blue curve is translated under the red curve, as in all heat exchangers there is a pinch point, that is to say that there is a minimum temperature difference in the heat exchanger. So this pinch point gave the name of the pinch method of the analysis. So when the curves are close together and reach the pinch point, it is possible to see a green zone, a green area, where the red curve covers the blue curve. This green area is the internal energy recovery potential of the process. What does it mean? It means that if we best associate the hot stream with the cold stream, that is to say, if we design a heat exchanger network between this hot stream and this cold stream to recover this green area, we have this heat duty, this green zone. We will reduce the hot utility and we will reduce the cold utility if we implement this heat exchanger on the network. If you want to go further on the pinch analysis, on the energy pinch analysis, I just insert a link for YouTube video about a webinar about the energy pinch analysis, so in the field of the energy. This link explains the construction of the curve and how we use our tool at ProSim to propose a new heat exchanger network in order to increase the energy efficiency of a plant. So from a water point of view, it is exactly the same concept that is used. Indeed, the concept of sink and sources is used. For a given process, there are water needs that are called, in fact, sink in red, and we have discharges, wastewater that come out from the process, and these discharges are named the sources in blue. With the energy pinch analysis, it was necessary to associate the hot stream with the cold stream in order to exchange thermal energy, and heat duty. For water, the mass for the mass pinch analysis, the principle remains exactly the same. You have to best associate a water need with a water discharge, a sink with a source. Water is feeding the process with a certain quality of water, and we will replace this stream of water with all the stream of a wastewater of the sources. To design a new water network, it will be necessary to associate the different needs with the different wastewater stream, and normally at the end of the generation of the water network, we will still have some discharges, but they are more loaded, and there will still be more water requirement, but these water requirements are less in quantity compared to the initial situation. If we want to just summarize this analogy between energy and water pinch analysis, it is possible to propose you this just table. For energy, we talk about Heat transfer, for water, we are talking about mass transfer, pollution. The quality indicator in the field of energy is the temperature. We classify the streams according to the temperature. For the water, it's the purity in general. That means we talk about contaminant, concentration of contaminant. So for energy, the transfer is involved is the thermal heat duty for the cooling, for the heating, and for water, it will be the transfer of pollution. And finally, what we seek to minimize for energy is the utilities. We try to minimize the hot utility, the cold utilities for energy. And for water, we try to minimize the needs of water, the input of water, and also the waste water. So we try to limit the discharges and to try to reduce the water inputs. So we saw the analogy between energy and water, and I will present you the objective and the expected results for the water pinch analysis. So the main deadlock when one wants to reuse a discharge, even partially to replace a water need, is the level of contamination. It is because that there is pollutant, there is contaminant in the discharge, maybe one or several pollutants that we are not able to reuse some streams. So usually the water entering in the process, and then this water is concentrated in contaminant when the water is used in the process. The output stream, the sources, are in general more loaded in contaminant. In fact, the first step is the identification of the different pollutants, the different contaminants. It means the identification of the contaminant which limits the reuse. And then, like an energy analysis, we will use the purity of the water in terms of quality of the streams, and we use the flow rate of water in terms of quantity in order to apply this water pinch analysis. So concretely, for an industrial site, first, it will be necessary to determine the sink and the sources of the processes of the process. That is to say, the water needs and the discharges. We must define a scope for the studies. That can be a local scope at the scale of a workshop or a global scope for the entire factory to acquire this data collection. And then it is necessary to determine the contaminants limiting the reuse during this data collection, during this data recovery. It is the most critical part of the pinch analysis. For the rest, the construction of the composite curve and the results, we will see that it's mathematical, it's systematical method, it's really simple and really easy to understand. So the crucial part is the data collection. You cannot do mistake when you perform this pinch method. The problem is generally the data. So for each stream, sink or source, it is necessary to collect the flow rate of each stream, which are generally noted F, and the concentration in contaminant, called C. And knowing this information, it is possible to draw water requirement and water discharge in a mass load diagram according to the mass flow rate. So the formula is relatively simple, and we just note that the slope coefficient is equal to the concentration of the stream. So we can start with just a simple process with just one water input and one output, one sink and one source. So the discharge streams from the source is less concentrated because of the slope coefficient, but the flow is more important than the need of water, than the sink. So this example is very practical. Is just to understand a little bit what is about in the water pinch analysis. So as we did previously for energy field, we draw our two streams, our sink stream, our need of water, and our source on the same diagram, purity according to the mass flow rate. And then we will try to place the discharge curve in blue under the red curve of water needs. The concentration of the discharge must be less than or equal to the concentration of the water requirement, of the water input, in order to reuse a discharge. So the blue curve is necessary under the red curve, as we did for the energy field. So for this example, it is possible to see that the red curve covers the blue curve, and there is also a green zone, a green area that is called the maximum water recovery, MWR. It is the maximum of water that could be reused if a reuse is implemented between these two streams. So concretely, with our process, it will be able to reuse part of the discharge stream to completely replace the water supply in red. So it's a very simple example, but it's just important to understand the method with a simple example. For an industrial process, it is not more complicated. It is just necessary to make the inventory, the data collection of the different streams that have different concentration in contaminant, and then in the diagram mass load according to the mass flow, we will place the different stream from the less concentrated to the most concentrated stream. So we sort the stream. This allows us to build the composite curve for the water need. It is named the sink composite curve, like in energy field. For discharge, the principle of construction is identical. And with these two composite curves, we can move the blue curve horizontally so that the blue curve of the discharge is under the curve of the need. It is necessary to have sources to be less concentrated than water input, than water requirement, in order to implement a reuse, to make the reuse possible. When the curve touches the pinch point, a green zone, a green area is obtained, like in the energy field. For this green area, the red curve completely covered the blue curve. This green zone is the maximum of water that can be reused within the process if the sinks are best associated with the sources with an efficient water network. This construction, like an energy analysis, is used to calculate the minimum wastewater flow rate of our process, which is often noted WW, and also the flow rate of fresh water, that is to say the water needs of our process as a minimum, the minimum water requirement that is regularly noted FW for fresh water. So if I just do a summary of the pinch analysis, we see that the pinch method is used to draw the composite curves. The most important information is the potential of improvement, that is to say the possible improvement of the process. For a given process, it is possible to calculate the maximum consumption if there is no reuse in our process. This is the current situation, the current case of many industrial processes. And on the other side, we will be able to place the minimum water consumption if we had a water network efficient at 100%. What does it mean? It means that if we have a network which recovered 100% of the green zone, we have this minimum of water consumption. And then we can compare the actual consumption with the minimum consumption if we have the best network in the process. And so we can calculate the potential of improvement that it's possible to reach. And this method is really interesting because we can use it to quantify the water saving. We just perform the water pinch analysis and we are able to know if there is an improvement or not, and then to quantify the water saving, so the gain. After, it is possible to go further with this pinch water analysis. The main result is the water saving, as I showed you previously, but then you can go further. But normally, the main advantage of the method is that the operating conditions, the operating parameters of the process are unchanged, are not modified normally. But sometimes it is interesting to change operating conditions, for example, the purge rate or the maximal concentration for water input on each equipment. So if we want to go further, we can imagine to modify this operating condition. Sometimes it's possible to have substantial gains just by modifying some parameter. For example, the limits of concentration for equipment. So for example, you have an equipment operating with just fresh water, drinking water on the input, and maybe if we replace the fresh water by a water flow rate a little bit more pollute, the process will operate correctly without any consequences and no impact for the quality of the product. And we will do really huge water saving with this method. And sometimes it's possible to propose regeneration treatment unit in order to reuse the discharges. So these techniques are often promising to go further, but it must be understood that it's necessary to have the agreement of people on site before trying to propose one of these solutions, because generally operators are a little bit reluctant to make this kind of modification on the process. So if I try to sum up all this information about the water pinch analysis, the different steps are first, the inventory, the data collection of water needs and of the discharge of the sources. That is to say, to define a scope for the studies and then recover all the data for all the stream and for all the contaminants. The contaminant that limits the reuse. There may be one contaminant, but it can be several contaminants in the problem, but in any case, all the measurements are needed. And from this data collection, we can apply this pinch method. We can obtain a diagnosis, that is to say, we are able to know if there is a margin of progress compared to the minimum. It is the main interest of the pinch analysis. The inventory and the data collection are the most critical part, the critical phase, and the pinch method instead, it's a mathematical step, it's just systematic and automatic method, so there is no particular problem for these steps. The same observation is done, in fact, for energy audits and water audits. The problem is to get the data collection, the inventory data. Indeed, often we do not have necessarily all the data, and it is necessary to make reconciliation of data. It's necessary to make additional measurements on site, and therefore this step is probably the longest and toughest step for the pinch analysis, and it's the less obvious task. So during this inventory and this measurements collection, it will be necessary to determine which is or which are the limiting contaminants for reuse. So in industrial effluent, normally they are composed of several contaminants in general. Nevertheless, we generally observed with our experience in the field that it's possible to identify the most limiting contaminant. This can be an aggregated contaminant like the BOD, the biological oxygen demand, or the COD, the chemical oxygen demand, or another specified contaminant. In all cases, it's generally possible to reduce the analysis to a monocontaminant pinch analysis. And this first monocontaminant pinch analysis will propose some solution. We obtain a first water network, and then once we have this first water network with just one contaminant, it is possible then to check that the concentration of other contaminants are under the limit, under the threshold for the operating of the process. So this slide just shows some the main indicator in the field of food industry. These indicators are used regularly in the field of the food industry, and the food industry, in fact, it is a big consumer of water. So as I said previously, the data collection is the crucial step. It's the most important step, in fact, and we can only advise you to build simulation of your process. That is to say, to create a digital twin of your process, of your factory. Why it is interesting to build a simulation of our process? There is different things. The first is to build a file in which we will have all the information, the data collection for the audits, but also information about sizing, operating condition. This simulation can be used to guarantee a consistency of the material balance and the energy balance. This will also overcome the missing data from the process and the missing measurement. We can use the simulation for data reconciliation and to predict results. We will be able to validate the water network proposed by our tool, Simulis Pinch. And finally, we will be able to calculate cost and return on investment directly in our tool. So our tool for our simulator is named ProSimplus. ProSimplus Simulator is therefore a good tool, very complementary to an advanced pinch analysis, energy or water pinch analysis. So if you want to go further, I describe here some interesting references on the subject of the pinch method, energy, water, and mass pinch analysis. Now I am going to introduce you Simulis Pinch tool, and Simulis Pinch is used to generate new water network, more efficient water network. So if I just take the scheme for the pinch analysis, an inventory must be performed, and then we can apply the pinch analysis. With the results of the pinch analysis, we have a diagnosis. Therefore, we just calculate a margin of progress. The pinch method does not provide a water network. It only gives you a diagnosis. If you want to go further, if you want to obtain a water network afterward, you need a tool, and for example, you can use Simulis Pinch in order to reach this optimum. So in few words I have just few words about Simulis Pinch before the demo. When you just buy a Simulis Pinch license, you have access to two modules. An energy module for energy, for the energy pinch, for the proposition of heat exchanger network. This part is about energy efficiency. And you have a water module for generation of new water network. So in fact, you just have access to the two different methods and to the two different tool, water and energy tool, in just one tool, Simulis Pinch, and in the Excel environment. So for the demo, I present you just a chemical process, or it's a chemical example. The process is simple with reactor separation units. It's a classical process. And for this process, there are different water needs, needs for the boiler, needs for the scrubber in red, the red point. And there are also wastewater that are concentrated, especially in ammonia. So in blue on the diagram, there is the sources. The ammonia is the limiting contaminant. That is to say that the ammonia limits the reuses within the process, especially for the scrubber and also for the boiler. So if I sum up the data collection, there are two things. The actual water consumption is 7 kilograms per second for the scrubber and for the boiler, and there is also 4 sources as displayed in this table. So I will extract this data and I will use Simulis Pinch in Excel. So I will just show you the demo for Simulis Pinch in Excel. So I will use the same data. So I have the two sinks, one for the scrub, one for the boiler. So 2 input, 2 sinks, and 4 sources. So it's just the data collection. We just measure the mass flow rate in kilograms per second and also the contamination of ammonia expressed in ppm. So the value for the flow rate, for the mass flow rate, is positive for the sink, it's an input, and negative for the output for the sources, for the discharge. And so I will use our software. So I will go in the add-ins tab and I will run Simulis Pinch Water. So the first steps for the use of Simulis Pinch is to define the type of analysis. So if we use a mono-contaminant analysis or a multi-contaminant analysis. So in this case, we just have one column for the ammonia, so it's a mono-contaminant analysis. So I choose just mono-contaminant analysis. And then we have to define the data definition. So as I explained you previously, Simulis Pinch can be linked to ProSimplus, to our simulator. So in this case, you just have to select data from ProSimplus and we just do directly the link between the simulation and the tool in Excel. So in our case, it's just raw data because the measurement of the flow rate, of the mass flow rate and the concentration are directly filled in the Excel sheet. And so then I have to select the data. So I select the flow rate and the concentration. Then I have to fill the mass flow rate unit. So actually we are in kilogram per second, and for the unit it's expressed in ppm. So for the first part of the demo, I just let remain this box unchecked, the water network analysis. And if I just click on calculate, in fact, the software will just perform the water pinch analysis. The software just do the diagnosis of the process. So the main results are summed up in this sheet. So there is many information, many interesting information, but as I present you in the presentation, the main results are the composite curve. So there is the composite curve for the sink composite curve, and also the sources composite curve. So I can say that for the sink, there is the two inputs, the boiler and the scrubber. The slope coefficient for the boiler, it's 0 because we want fresh water for the boiler. And for the scrubber, there is a concentration, a limit of concentration for the scrubber. And the same for the sources. And we can see that there is a green area, there is a green zone in the middle. And so there is a maximum of water that we can reuse. So actually we can reuse approximately 5 kilograms per second. So what does it mean? It means that on the process, we can find a water network which recover this 5 kilograms per second. And at the end, normally, the process will just consume 2 kilograms per second. Actually, the process consumes 7 kilograms per second for the boiler and the scrubber. But if we build a water network efficiently, normally we will recover all of this green area and we will reduce the fresh water, but we will reduce also the waste water. So if we want to get this water network, we have to rerun the tool. So we go in the add-ins tabs and I click on Simulis Pinch. I reselect the data. The units, it's correct for the mass flow rate and for the measurement. And I check the box water network analysis in order to design a new water network. So this interface, this first window is proposed. I will not describe all the options, all the functionalities. I just do a general presentation. So on the top part of the windows, it's about the constraint of the site. It means that if you want to add some constraint for the design of the water network, you can. For example, if you want the software, if you want Simulis Pinch to propose you only reuse with big flow rate, for example, with a flow rate of 2 kilograms per second, you can change 0 by 2. In this case, the software will only propose you reuse with more than 2 kilograms per second for the flow rate. You can express the limits with a direct mass flow rate or also with a minimum percentage compared to the green area, compared to the MWR. So there is different option for the constraint. And then for the water design, the tool, Simulis Pinch, will select the reuse according to selection criterion. So you can choose the different criterion you want. So the first one we use, it's the maximum factor of flow rate and efficiency. But you can change. If you want the software, if you want Simulis Pinch to choose the reuse with the maximum efficiency in first, you can just change the criterion selection. So you can change the criterion selection, and then you can change also the stop criterion. So actually, the software, Simulis Pinch, will run until it reaches 100% of the green area. That means we try to reach the green area and we try to reach the optimum. If you want to reach, for example, 50% of the green area, you can fill the value and the software will stop when it reaches 50% of the green area, of the maximum water you can recover. So for this demo, I just remain with 100%, and I run the software, and the software stopped and he stopped with a message. So he informed the user that we recovered 100% of the green area. So the Simulis Pinch proposed us a new water network which recover all the entire zone of this green area. So we will see what it's about. So the main result sheet is named the water network results. So you have a summary of the network. So we know that actually the network proposed by Simulis Pinch recovered 100% of the green area, the initial green area. And the software will propose us just 2 reuses. And the 2 reuses are described here. So there is 1 reuse between the input for the scrubber and the discharge from the off-gas condensate, and the other reuse is between the boiler for the input and the distillation bottom from the column. So for the 2 reuse, there is all the characteristics. So the characteristics are on the right here in green. So we know that for the first reuse, we used approximately 4 kilograms per second of the sources, and we mixed with fresh water in order to supply the scrubber. And for the second one, for the boiler, we use 0.8 kilogram per second of the sources to fill this input need. So this is a table of results. There is many results, and I think the best result is the water network. So I will just change the size of the text in order to be more readable. So just let me 1 second. So to explain you this water network, on the horizontal line here, there is the input of water of your process. So actually there is 2 sinks, there is 2 input of water for the boiler and for the scrubber. And there is 4 sources. So the sources are displayed in vertical here. So as we can see, there is 2 reuse. The first reuse is the reuse of the distillation bottom here. They are used to replace part of the fresh water of the boiler. And for the scrubber, we use partially the off-gas condensate here. We reuse 4.1 kilogram per second for the scrubber, and we mixed with a little bit of fresh water in order to replace this water input. So there is 2 reuse, and as we can see, with just 2 reuses, we are able to reach the minimum of fresh water. Actually, with this new water network, the process will consume only 2 kilograms per second instead of 7 kilograms per second initially. So this is the water network without any constraint, in fact, but in reality, on site, there is some constraint, and you can add this constraint in our software. So to add this constraint, I will rerun Simulis Pinch, and I just will show you the different constraints you can add. So there is different constraints: zone constraints, mapping constraints, difficulty, and incompatibility matrix. So to use this constraint, you just have to generate the table. So when you generate the table, we will reuse the same data, but you are able to add some constraints. So for example, if you want to use zone constraint, you can fill a zone for the different stream. So for example, like that. And you can ask to the software to just propose you reused with sources and sink in the same zone. So this is about a workshop or a local zone. If you want to go further, you can directly fill the coordinates of each stream, and you can then fill the maximum distance you want between each sink and each sources. And in this case, the software will not propose you a reuse with a distance which is higher than this maximal distance. And there is also other constraint, like for example the incompatibility matrix. So it's the case, for example, when you want to directly ban some reuse. So for example, you don't want to reuse the distillation bottom in the boiler. So in this case, you had an incompatibility between the distillation bottoms and the boiler. So this is a short demo, and if I just come back to the presentation, with these results in Excel, we can go back to the process. We can also simulate the new process, the new water network in ProSimulis in our simulator in order to check that all are working properly and to check the different parameters of the reuses and also to calculate OPEX and CAPEX. But if we just model this process in ProSimulis, or if we just draw on a process like that, we have just two reuses. One is for the reuse of the water from the reboiler to the boiler, and the second one is between the output of the drum and which is feed the scrubber. It is a more pragmatic example just to explain the pinch method and the tool. We agree that for an industrial plant, before reusing water for the boiler, we will certainly be made a pretreatment, a regeneration to treat the water before feeding the boiler. So as I told you previously, every time the software proposes you new reuses with a new water network, it is necessary to check on site that everything is possible. If you perform a monocontaminant analysis, it is necessary to check that there is no problem with other compounds, with other pollutants in the discharges. So in summary, with Simulis Pinch, you have an autonomous tool in Excel, but this tool can be linked to ProSimulis to automatically extract all the data from the software. We saw that it gave you quick results. So I do just a demo for 6 streams, but with 20 sources and 20 sinks, the result will be also quick. It will not spend more time than the example of this demo, in fact. That is not the case of other existing tools on the market. Generally, tools on the market are based on optimizers. Sometimes they do not converge. Sometimes they converge, but with unsuitable solution in industry. So with our tool, there is a great flexibility at the level of the configuration. That is to say, you are able to add different constraints, distance constraint, incompatibility constraint. It is really possible to configure the tool with the constraint of the factory. And this tool is an Excel tool, so you are able to write your own formula, to write your own program if you want to go further and further. So to conclude, we have a long experience in the field of the pinch methods of the pinch analysis at ProSim, and in particular for the energy and water pinch analysis. ProSim has a team of experts in the field of energy and water audits with the water and also with the energy pinch. This method can be applied not only just in food industry, but also in chemical industry, in refining, in pulp and paper, in different type of processes. And usually with this type of method, we can reduce water around 10 to 20%. In some cases, we reach 40%. And finally, for the return on investment is just piping, just pump. So in first approach, we've just only reuse without any regeneration, without any intermediate treatment. In general, we have a return on investment lower than 1 year. So the technology and the methods are mature. We have tools to perform this energy and water audit. This method required a little bit of expertise. That's why you do not hesitate to contact our services, and we have training on our tools, so do not hesitate to contact us also if you are interested on this subject. So if you have any question and answer.
Okay. Yes, we have several questions actually. The first one, how pinch DT mine is related to DT in different exchanges? In other words, does DT for exchanges have to be lower than pinch DT mean?
So it's an energy pinch question. So it's about the minimum DT in each heat exchanger. So in fact, when you build the composite curve, the user feel a DT, temperature, different temperature for the construction of the curve. But then for each heat exchanger, we will use the same DT. In fact, so it's the same DT as the pinch method we used for the design of the heat exchanger network.
Okay, another question for water pinch. We do not have deconcentration mean like DT mean in energy pinch?
No, yes, for sure. For the energy pinch, we have a DT. We reach the DT in order to do the transfer of energy. You can touch the curve, the two curves together, but in this case, the surface area of the heat exchanger will be really high. So it's not the case in general. For water, is different. You touch the curve together because there is no difference of quality needed to do the transfer. For a transfer of material, you just mixed the two streams. You mixed your sources with fresh water in order to replace a sink. In an energy domain, it is different. You don't mix the two streams, you just do an exchange on each part of the heat exchanger. That's why there is a DT for the energy pinch and there is no DT for the mass pinch analysis, for the water pinch analysis.
Another question, how can we do a pinch analysis with multi-contaminants?
So yes, I don't present you the multi-contaminant analysis, but in fact, it's not really complicated. In the Excel sheet, if you have several contaminants, you just have to add the different columns for the different contaminants. So if you have 4 contaminants, you have to fill the 4 columns of each concentration of each contaminant. That means that if you do the data collection, you have to measure all this data on the plant, which is probably the longest and toughest part and difficult part. So that's why generally we use a monocontaminant and we just get some results and we try to do the reuse and we compared with other contaminants. But generally we can just determine the most limiting contaminant. But with Simulis Pinch, it's possible to do a multi-contaminant analysis, and the software will propose you, each time it will propose you a reuse which satisfied the level of concentration on each input, on each sink of your process. So it's just material balance, in fact.
We are over the hour, but I'm going to take one last question. Can we combine energy pinch and water pinch simultaneously?
Yes, in fact, not simultaneously, but one after the other. That means generally we do an energy pinch analysis because it costs a lot compared to just water. So generally, it's first energy and then water. But generally we do just energy or water, but in a case you want to do the both, you have to choose the best suitable process to improve your process. Generally, there is a nexus between energy and water. That means if you improve the energy, you also improve the water consumption. So normally they will give you good results. So you can start with an energy pinch analysis and then go on the water pinch analysis. The results are improved in any case. So there is no fight on this subject.
So thank you for attending this presentation. We hope that this webinar met with your expectation. And you have more information on ProSim website. If you have some more questions, you have a contact form on the website. It's www.prosim.net. We remain at your disposal, and I wish you to have a nice day. Bye.
Bye-bye.